When you upload a photo or stream a movie, that data doesn't float into the sky, it dives underwater. The cloud is actually a massive physical machine, largely made up of heavy cables resting on the ocean floor, connecting continents across thousands of miles. To move billions of gigabytes across these distances every single second, traditional copper wires are far too slow. Electrical signals degrade and lose strength rapidly over long distances. To meet the demand for speed and volume, engineers had to find a faster medium. They turned to light. But natural light is completely chaotic. Turn on a flashlight and the beam spreads out, hitting dust and air molecules, weakening as it travels. You cannot use a scattering, disorganized wave to encode precise information across the Atlantic Ocean. To build a global communications network, human engineering had to take this raw, untamed physics and force it into absolute obedience. Think about the light from a standard bulb. It radiates outward in a disorganized mess of different wavelengths and directions. It is too noisy to carry a clean signal. The solution to this chaos is the laser, an acronym for light amplification by stimulated emission of radiation. Inside a laser, we manipulate light at the quantum level. Through a process called stimulated emission, a specific particle of light hits an excited atom, forcing it to drop its energy state. As it drops, it releases a second photon that is perfectly identical and perfectly synchronized to the first. This sets off a chain reaction. Billions of photons multiply, locking into step with one another. They form coherent light, a single, intense beam traveling in a perfectly straight line without spreading out. The theoretical framework for this level of control was established in the mid-20th century by physicists like Charles Townes, who mapped out exactly how to stimulate and harness this radiation. With coherent light, engineers finally had a microscopic vehicle. They had a disciplined beam capable of carrying a signal across vast distances intact. But a laser beam naturally wants to travel in a straight line. If you want to route that light from New York to London, you need a physical pipe that can bend and curve along the ocean floor. The answer came in the form of fiber optics. Researchers like Narinder Singh Kapani demonstrated that you could successfully trap light inside long, thin strands of glass. This sounds counterintuitive. Glass is transparent. If you fire a laser into a curved glass tube, the light should shoot straight out the sides at the first bend. Looking at this diagram of an optical fiber, you'll see two layers, an inner core and an outer cladding. The trick relies on the refractive index, a measurement of how much a specific material bends light. The core is manufactured to have a slightly higher refractive index than the cladding wrapped around it. Because of this specific difference in density, when the laser beam hits the boundary between the core and the cladding at a shallow angle, it doesn't pass through, it snaps back. This physical phenomenon is called total internal reflection. It turns the boundary into a perfect mirror. The laser bounces relentlessly down the length of the fiber, completely trapped inside the glass core, no matter how the cable twists or turns. By manipulating the refractive index of the glass, human engineering forced chaotic light into a designated lane, creating an enclosed optical highway. We have the disciplined beam, and we have the physical highway. The final step is turning that trapped light into complex human information. Digital data is simply a sequence of ones and zeros. To send a file, transmitters act as an ultra-fast strobe, pulsing the laser on for a 1 and off for a 0, billions of times every single second. This optical strobe operates at frequencies far beyond the limits of electricity. A single glass thread, thinner than a human hair, can carry millions of times more data than a standard electrical pulse. Taking the mathematical principles of information theory and executing them by bursts of laser light inside mirrored glass is what allows a global network to function at scale. At the other end of the cable, a sensitive photodetector catches these microscopic flashes. It decodes the billions of pulses back into electrical signals, instantly reassembling them into bank transfers, video streams, and text messages. Every time you load a web page, you are commanding a physical laser to fire. You are sending a pulse of coherent light bouncing down a glass corridor across the bottom of the ocean, all in a fraction of a second. The cloud relies on laying thousands of miles of armored cable, amplifying signals across vast stretches of water, and executing quantum mechanics on demand to bend the laws of nature to our will. Our entire modern digital existence rests on this infrastructure, a machine built entirely out of mirrored glass and disciplined light.